So to give you a brief overview of the work we do in my group, we are interested in doing quantum many-body physics with what are called gases of atoms and molecules. So what we do is we basically engineer these Hamiltonians, which are theoretical Hamiltonians, which can be used to describe electronic models in condensed matter physics. So they describe materials like these high DC superconductors or moire materials or quantum magnets, where in these materials you have these strong correlations between the electrons, which give rise to emergent phenomena, to new types of phases, with exotic properties that might be useful for technological applications. And we are interested in understanding these materials through these models from a microscopic point of view to better engineer their properties. So most of what I'll be talking about today is going to be relevant to these moire materials. Okay, so the platform here is these cold atoms in optical lattices. Optical lattices are basically potentials that we create through the interference of laser beams in the lab. And in this quantum simulation, basically the atoms are playing the role of the electrons in a solid, and the optical lattice is playing the role of the ionic lattice in a solid. So we can think of this as an enlarged model for condensed matter physics, where we blow up the system by about 4 orders of magnitude. The length scales here are on the order of the wavelength of light, so about half a micron or so. And the benefits of this platform are, first, the Hamiltonian we write down for the system is very well understood from the microscopic level with the precision of atomic physics, unlike the crude models that people use for condensed matter systems. And furthermore, we have control over all the parameters of this Hamiltonian, often in real time. So for example, you can control the tunneling of the atoms in the optical lattice, changing the laser intensity, or control the scattering of electric atoms to control the interactions. These are very clean systems, unlike in condensed matter again, where we don't have impurities, we don't add disorder, we can do it in a very controlled way. The dynamics is very slow, typically on the millisecond time scale, so it's very easy to access in the lab. And most importantly for this talk, this large spacing in these systems means we can actually optically image and manipulate the system down at the smallest possible length scale, the smallest relative length scale, which is the single left side. And this is the essence of this technique called quantum gas microscopy, which is now used by many groups around the world, which allows us to basically study these correlated systems at a single site level. So this is a picture from my lab where we're looking at lithium-6 atoms. This has been done with many different bosonic and fermionic species. Lithium-6 happens to be a fermion. You're looking at a two-dimensional gas with hundreds of atoms in it. And we can prepare the generate Fermi gas and then adiabatically load it into the optical lattice to quench the kinetic energy and basically bring out the effects of the interactions. So this allows us to prepare a many-body state, and then we can proceed to characterize the state through the endpoint correlation functions with this microscope. So what we do is we suddenly turn on a very deep lattice, freeze all the tunneling in the system, and we project this many-body state, which is a superposition of many states and phases of measurement, onto a particular realization in spin density, and then we can extract these endpoint correlation functions that characterize the state. Okay, so the natural family of Hamiltonians that these quantum gas microscopes study is Hubbard Hamiltonians. These are Hamiltonians that are paradigmatic Hamiltonians for studying strongly correlated electrons in a lattice. Here I show the Fermi-Hubbard Hamiltonian that describes basically two species of fermions loaded into an optical lattice. Those are two hyperfine states of the atom in our case, in analogy to the spin-up and spin-down of electrons. And there are two terms of the Hamiltonian. The fermions they live in the lowest band of the lattice, and they can tunnel between neighboring sites with matrix element T. And then if you have two fermions land on the same site, they have opposite spins, they will have a strong one-site interaction E. So this is the kinetic term here for the hopping, and this is the interaction term. And it is basically the competition between these interaction and kinetic energy that gives rise to all the richness that traces matter can give these fluid systems. this type of Hamiltonian was first proposed by Phil Anderson way back as a model which can be used to understand the high DC superconductors shortly after their discovery. So there's been over 4 decades of work trying to understand the ground states of this Hamiltonian. But it's very challenging from the point of view of numerics at low temperatures, trying to understand the phases that emerge. And that is the point why we're trying to do these quantum simulations. Now, most of this talk is not going to be focusing on the squared axes, which are relevant for the cuprates. I'm going to be looking at other lattice geometries. But basically, most of the early work so far, the overwhelming amount of work in the cold-atom community has been focusing on the square lattice because of the connection to the cuprates. So I'd like to just give you a few highlights of that work that has been done with microscopes. So in these systems, we get the simplest point to start at is half filling or no doping in the system. So this refers basically to the point where we have an equal number of particles at sites. So typically we're working at a regime of strong interactions which suppress density fluctuations in the system. And what that leads to is a parent compound called a multi-cylinder, where essentially we have one atom per site in the lattice because of the strong interactions that suppress double occupancies. And these you can see in these microscope images. Now, if you lower the temperature further below the interaction energy scale, you can get now ordering in the spin sector. Remember, there are 2 spin states here, and the spin can start to order the system, and this is due to super exchange processes. So you saw in the Hamiltonian, there is no direct interaction between different sites, but super exchange refers to a virtual process where basically an atom hops to a neighboring site. This is an off-shell process because there's a strong interaction energy when you have a low occupancy. So it can't stay there for long, it hops back. So this is a second order process in perturbation theory, which is of order t squared, the Tony matrix element squared over the interaction energy. And so that's roughly the scale of the super exchange constant. And we can describe the system in this regime in terms of an effective Heisenberg model with these super exchange interactions, which are antiferromagnetic. And this leads to, at low temperatures, when you're well below the super exchange temperature, to this long-range antiferromagnetic order that has also been observed in these experiments. Now, these 2 phases here, the one-slater and the antiferromagnet, we understand them very well. We know from quantum Monte Carlo calculations that they are there in the Hubbard model just like they are there in the cuprates. And the calculations tend to be doable in the regime of half filling, but where the Monte Carlo becomes very difficult is once you go to a doped system. There it becomes very hard at low temperatures, and that's where really all the interest is in doing these quantum simulations. So there's been a lot of work on these doped systems over the last few years with microscopes. And here are just a few highlights. So this is work, for example, from my group, where we're looking in the normal regime, not in the superconducting regime, we're looking in the normal phase for anomalous transport properties of the doped system, of the doped multi-insulator. And so what we observe, for example, in this experiment, is that the resistivity is linear in temperature, which is something that's the Kinetically community refers to as a strange metal, and it is observed across a wide range of correlated materials like the cuprates, snaketides, and so on. It wasn't known before that it exists in the Hubbard model, and here this quantum simulation gave us that information. Other experiments here have also studied transport, but focusing on the interplay of, say, a single pole with the antiferromagnetic ordering. So those are experiments from Harvard and Munich, where they were asking how does the hole, if you put a hole in the system and let it move, it's a mobile hole, so let it move in the antiferromagnet, how does it disturb this antiferromagnetic order? And one of the things we see, for example, here is that you can start with the hole, it moves around, and it breaks bonds in the antiferromagnets. So as it moves away from the spin-on it leaves behind, there's a string that forms, these so-called geometric strings, whose energy grows linearly with distance. So the hole cannot move very far from the spin-on, and you form this geometric string, a bound object whose scale is on the order of the super energy scale is on the sort of the super exchange energy scale. Now, you can think of the string, it really has vibrational modes, rotational modes, and so on. It's a quantum object that fluctuates quickly because the motion of the hole is fast compared to the spin on its bound to. And you can now look at also an average picture through higher order correlation functions like 3-point correlation functions to image basically the disturbance in the antiferromagnet that results. And this is the so-called magnetic polaron in this Hubbard system, the doped Hubbard system. And this was directly observed, for example, in the group. Okay, so this is very strongly related to what I'll be telling you about now, not on the square lattice, but on a different lattice geometry, the triangular lattice. So the step that we have made in the lab recently is we're now moving towards programmable lattices. We've played around a little bit with tweezer arrays to make these programmables. Here I'm going to be focusing more on interferometric programmable lattices. So this is the lattice that was first introduced by the group of Manuel Bloch in their Waseem microscope, and we've implemented it also in our fermion microscope. I'm not going to go into the technical details, but roughly speaking, what we're trying to do here is to access many different types of geometries within the same setup by just controlling parameters in software. So for example, you can start with a square lattice that is created using this laser beam here, the orange one, and then superimpose on it an uninterfering one-dimensional lattice. And you can control the relative phases of these lattice patterns and the relative depths to access a wide variety of geometries. For example, triangular lattices, honeycomb lattices, these coupled 1D chains. And if you supplement this with a digital micromirror device, they've also shown you can realize lead lattices with flat bands, Kagome lattices. So all the different ingredients you might be interested in, like frustration, flat bands, topology, etc., can be accessed with this setup purely with software. Okay, so I'm going to be focusing on a particular geometry in this talk, where we're going to go between a square geometry with tunneling T between the nearest neighbors, and now we're going to open up a tunneling along one of the diagonals, which is T prime. And we can vary this ratio of T prime to T at will. So if we have T prime 0, it's a square lattice. If these two are equal, the connectivity of this lattice is that of a triangular lattice. Okay, so why is the triangular lattice interesting? So it's interesting even at half filling without any doping already. So at half filling, just like the square lattice, if you work in the regime of strong interactions, you'll get a multi-insulator. But then, if you ask, okay, what is the order of the spin sector, that's already very interesting because on triangular plaquettes, you have the phenomenon of spin frustration. So for example, if you put a spin down and a spin up on these sites, then you cannot decide what to do with the third spin. Okay, so here's a cartoon phase diagram, a quantitative one, of what sort of phases you might expect at half filling as you vary this ratio of T prime to T and the interaction strength. So again, if you work at T prime 0, you're in the square lattice where you have this Néel order, which we understand pretty well. But then as you increase T prime, for example, when it's equal to T, you have a triangular lattice. And there, as you increase the interaction strength, there is a transition between some sort of metallic phase at weak interactions. At very strong interactions, you get a multi-insulator, which is now again described by a Heisenberg model. And then it turns out from the triangular lattice model, it is known that the Heisenberg model has a way of resolving this frustration by ordering the spins in the plane of the lattice in a so-called 120-degree spiral order. Now, in between, we don't understand what goes on very well. We know it's some sort of non-magnetic insulator. There's a lot of debate of what the phase is exactly at these intermediate interactions. And for example, these papers here, they think it might be some sort of spin liquid, which breaks time reversal symmetry. So it's a chiral spin liquid. And there are some also other interesting phases as you increase T prime and you enter the 1D regime. All right, so because of all this interest, even in the absence of doping, of course, when you add doping, things get even richer. So there's been a push in the community with these microscopes to go towards triangular lattices. So here are some recent results from the group of Peter Schaus at the University of Virginia and Marcus Greiner at Harvard. I think you might be hearing soon from Martin Lebras, also in this conference about the work they're doing there, where they measured 2-point correlation functions to characterize the antiferromagnetism that appears in the system in the strongly interacting regime, to basically look at these correlations that are Now let me move on to what we're doing with our microscope at Princeton. So the unique feature of our microscope is that usually with a typical microscope like the ones I've mentioned, you are not able to measure the full information of the system. So in a Hubbard model, on a given site, there are four possibilities. You can have a hole, a double one, an upspin, or a downspin. However, when you do this measurement, there are issues having to do with light-assisted collisions and so on. So the readout tends to be binary in these microscopes. So you only can read out two of these possibilities. Now, in this microscope that we're using here for our terminal microscope, we solve this issue by, before taking the image, once we form this correlated state, we've frozen it. Before taking the image, we use a magnetic field gradient to split the spin-ups from the spin-downs using a Stern-Gerlach B-field gradient. So now we can take simultaneous snapshots of the spin-ups and the spin-downs and extract the full information on the charge and the density in the system, which allows us to extract the endpoint spin and charge correlation function. So for example, we can start by reproducing these two-point correlation functions that you can see the spiral ordering that was seen in the previous work, but now we can go a step further. So in particular, we were fascinated recently with some work that has been coming from the Moiré community. So here, this is work from the group of Atash Imamoglu at ETH Zurich, where he's looking at these transition metal dicapotonites. So they're looking at a bilayer system of these transition metal dicapotonites, and they're twisting them. You might have heard of magic angle twisted bilayer graphene. Here, we're not working at any magic angle, just a twist. And what they're seeing here, what they realize here is a very clean triangular Hubbard system. Okay, so what they find in the system is they've been studying it versus doping, and they measure the spin susceptibility of the system, and they find that on one side of half filling, they have antiferromagnetic order. On the other side, they have ferromagnetic order. And there are reasons they suspect that this order is very different from the usual super exchange based, for example, antiferromagnetism that I showed you earlier. So here, they think they have a new kind of magnetism in the system that is called kinetic magnetism. And there has been a lot of work from theorists on trying to understand this magnetism. In particular, our collaborators, Eugene Dembler at ETH Zurich and his student Ivan Moreira, have been trying to basically build a microscopic theory of what's going on in the system. And they came to us with our quantum simulator where we have more microscopic access to test their theories. Okay, so the theory here is all based about an idea called kinetic frustration. And to explain that, let me start first with a single particle in a triangular lattice. Okay, so not an n-body system, very simple, just a single particle. So with this single particle, the Hamiltonian just has a tunneling term. So you have much simpler Hamiltonian in the Hubbard system, which is given here. Here's C dagger C, is you create and destroy fermions on sites. And you can ask, what is the ground state of the particle of this triangular lattice? Well, let me try to go through this a little bit contrived way. What I'm going to ask is, let me think about each bond. So we can assume here the sign of the tunneling is positive, and so the particle wants to delocalize on every bond. So it wants to form a spatially symmetric state. Okay? So it forms this spatially symmetric state. Here we can do this on the next one, on the next one, and here all the phases match in the symmetric state. So we can tile the entire lattice this way, and we find that the particle wants to delocalize over the entire lattice. So the resulting band structure looks like this, where because of this delocalization, the particle has lowered its kinetic energy by an amount -60, where the 6 comes from the number of near singulars. Okay, so far, pretty simple. Now let's look at the complementary situation. What happens if instead of a particle, we look at a hole in the system? So of course, for a hole, we need a background. So I'm going to choose a spin polarized background, which I'll loosely call the ferromagnetic background. So all the spins are pointing the same way. Now, it makes more sense here, instead of using these fermionic operators, to express this in terms of hole operators. Okay, so we use a hole operator. This is a hole patient operator that is basically destroys a fermion on a site. And we can make a substitution where we replace these operators with hole operators, and the C dagger C becomes an H dagger, but this is no longer a normally ordered Hamiltonian. So we can fix this problem by moving the operators to each other, but those are fermionic, and we have to anti-compute them. So we flip the sign of the system. Okay. So when we flip the sign, now we have to use these anti-symmetric orbitals because that's the ground state of each bond. And we can tile the system with anti-symmetric orbitals, but then when we put these two bonds here, the third bond cannot also be anti-symmetric. So what we find is that the system is frustrated, and we can no longer lower the energy of the hole as much as we did for the particle. So the minimum of the energy we can find by just flipping the best structure we had before, and it is negative 3T because this particle-hole structure, the best structure doesn't have particle-hole symmetry, so now the hole lives at these points where the energy is negative 3T. Okay, so how do we solve, so we say basically here the whole motion is frustrated in the system. This is very analogous to spin frustration, but it has to do with the motion of the hole rather than the spin. So how do we release this frustration? Well, we no longer work with a spin polarized background, we're going to flip some spins around the system. So let me show this in the simplest possible case, which is on a triangular plaquette. So we're going to start with a spin polarized background, introduce a single hole. And so here this is in the triplet sector where these are spin polarized. And we're going to try to write an effective single particle Hamiltonian for the hole, where the hole can now tunnel around this plaquette. And at the end of this process, the two spins here have exchanged, but they're in triplets, so nothing interesting happens. However, if we do this in the singlet sector, there when the hole moves around, we exchange the two spins, which are up, down, minus, down, up, and we get a minus sign. So this minus sign is exactly what's needed to cure the frustration that we had before. So we have a spin-Berry phase, which releases the frustration. And so what we've learned is that we create this polaron in the many-body system, where we basically have a hole that likes to bind to anti-ferromagnetically aligned spins, so anti-aligned spins. The binding energy of this polaronic object in this system is of order the tunneling, because I've never made any reference here to super exchange, so it's a high energy polaron if you wish. And there's been many predictions of this polaron over the past year because of this interest coming from the Moraine space. Interestingly, if you start with, instead of a hole, a doublon, there the system likes to bond to a ferromagnetic environment. The double likes to bond to a ferromagnetic environment because the double is like a particle, so it doesn't have the frustration. Okay, so how do we see this in the experiment? Well, we can go and evaluate D-point correlation functions. So for example, we can take a snapshot of our system and identify the dopants, the hole dopants, for example, and look at the spin environment. And what we find is around the hole, there are these anti-aligned spins, so there's negative correlation, which is exactly what we were predicting. Further out, we see some ferromagnetic correlations. We understand these, but I won't go into why that is sign first there. In contrast, around the double, we indeed find this ferromagnetic correlation. So this is what's called a Harter-Shastri polaron, after the names of the people who first discussed this in ferromagnetism. This is more in line of the Nagawaka ferromagnetism that was studied back in the 60s on square lattices by Nagawaka, and here we're seeing a more robust version of it that appears in the triangular lattice. Okay, so we can study these holes versus doping interactions. So here I'll just say make a few quick comments about this. So all the theory I explained works really well in the limit of large interactions in the multi-insulator. So in that regime, we find that as we dope the system away from half filling, initially we have a dilute gas of polarons. We have a few holes in the system. So you get basically a correlation function that scales linearly with the doping, because as you add more holes, the 3-point correlation function goes linearly. But then eventually the polarons start to overlap with each other and interact. So at that point, the scaling breaks down and you turn around. Okay, so that's the point at which we can think of this as a dilute gas of non-interacting polarons. Another interesting thing you see is that as we lower the interactions from the multi-insulator to the metallic regime, qualitatively some of the features remain there, but those in the regime of metallic interactions, this is no longer this Harter-Shastri polaron or or the Nagawaka Polaron, you can tell that partially from the fact that you're losing this linearity here. And also, I mean, we know we're not going to want this later because a single fraction in the system drops dramatically. Okay, so another thing to point out here is that in this system, because we're working at finite interactions, we have both super exchange magnetism and also the kinetic magnetism in the story. And what I was trying to explain here is that the kinetic magnetism, because it's of order T rather than J, it's a stronger form of magnetism. It survives to higher temperatures. So now we can understand the relative strengths of these different types of magnetism by evaluating instead of 3-point correlation functions, 4-point correlation functions. So the way we do this, for example, is we can take two spins and study the spin correlation function along a bond, conditioned on what's happening on the neighboring sites. So the neighboring sites, for example, could have two holes, a single hole and a single particle, or two single particles. So if you have two single particles, then to first order, there is no kinetic mechanisms at play here, because all you have is just super exchange. So the correlation we get in this case is very weak. Okay? By comparison, when we add one or more holes, we see that the antiferromagnetism becomes stronger, precisely because this is a T-scale effect rather than a J-scale effect. Which, of course, T is much bigger than J when you are working in regimes of interactions. Okay, so as an outlook for this is really the beginning of the story. We're starting to understand the microscopics of this kinetic magnetism, this new form of magnetism that has been discovered in the marine materials. There are more complex types of polarons that appear in these systems. For example, our collaborators Eugene and Devon have been predicting multi-particle bond states that can appear, where you have multiple magnons and multiple holes in the system that are binding together. So this might provide a way for hole pairing at T scale rather than J scale. So this might be a mechanism for high temperature hole pairing that we could look for in these experiments, and eventually these holes might condense and form a superconductor, as has been seen in some of these binary materials. Furthermore, we can also, what we've been doing in these experiments so far is just doing imaging of the polaron. Of course, it would be interesting to directly measure the binding energy either through spectroscopic techniques, or just a couple of weeks ago, there have been experiments where, from the Cornell group, where they basically apply the large Zeeman field in the system to break this antiferromagnetic polaron by polarizing it. And so you can at some point see, as you increase the field, there's a polarization plateau, which tells you about the binding energy. So we can do this, for example, in our experiments through imbalancing the gas, the spin imbalance to lead to an effective Zeeman field. So with that, I just want to thank the people in this work, Ben Spar, Max Pritchard, and Zoe Yang. We have other experiments in the group. We are looking at dipolar interactions with molecules, dipolar Hubbard systems. We have Rydberg atoms. I'm happy to talk to you about these. Thank
you. Yeah, great. So, yeah, we have time for some questions. People want to come up, or I can run to you. So I have a question about this Nagioka ferromagnetism. Traditionally, that's for infinite U. Can you?
Yeah.
But you're in a finite-sized system. Can you just comment on?
Yeah, I mean, the original Nagioka theorem from 1966 was a rigorous theorem that he proved for the infinite U Hubbard model with introducing a single hole. And what you saw there that you get ferromagnetism in the system. Now this theorem turns out once you add more than one hole, it all breaks down. And that's why Nagioka ferromagnetism has never been observed, except in one experiment a few years ago from a group with a single quantum dot cat with 4 sites. But in an extended system, it has never been observed. So ultimately, what causes the Nagioka ferromagnetism is constructive interference of the pathways of the hole. Now, in these triangular systems, the frustration turns out to actually cause, instead of being for the hole, it happens for the delta. And it's really a much more robust phenomenon. What we see from this quantum Monte Carlo, so what I didn't really emphasize, all the theory that you saw there is quantum Monte Carlo, which matches perfectly with the experiment. So what we see there from both the experiment, the quantum simulator, and the theory is that these triangular systems with this frustration, the Nagioka ferromagnetism is robust to finite amounts of doping, so it's really, you can do put a studies in a thermodynamic system, and it's also robust to strong interactions. It's very different from the story of the square lattices.
Why do you call it non-Yoka?
It's ultimately what happens with the gondola is the same physics. It's the constructive interference of the pathways. So it bears a lot of similarities, but it's not exactly the same set of the consideration.
Okay, so further questions? Okay, so then let's